So yeah, we are very happy to have Liviu continuing with the second lecture on locally conformally Kähler geometry.
Okay, thanks. I shall focus on LCK's potential now. It's a notion that Misha and I introduced. Um, I don't know if you see the title of the slide. Okay, now you see it. Um, it's a notion that we introduced, and I'm not happy to say that until now not many people use it, but I want to advertise for it because we have a lot of applications and results about it. So the definition is rather natural. You have an LCK and you look at its universal cover, the deck group, or at some other cover, it doesn't matter, and you ask that the scalar form be exact, but with a potential which is positive, strictly positive, and automorphic. So now you impose automorphicity to the potential, not only to the scalar form. And in this case, the Lie form will be exactly d log phi, and the pullback of the LCK form is normally is this one. What you can see immediately from the definition is that the notion is conformally invariant. Sorry. And if you remember the discussion about early Claus-Thoma manifolds, the condition about the automorphicity is essential. This is the definition. You have a scalar cover with the exact scalar form given by a strictly positive and automorphic pro-subharmonic function. The strict positivity, again, it is a problem. There exist examples. We have an explicit one provided by Matej Toma, but what we proved that is that if you can have all this picture with phi non-positive, then you can have it also with a positive phi. But it is a real theorem. It's not obvious, and it took time. There is an equivalent definition. Now, in this second talk, I'll be more specific and I'll give you some technicalities. This is important because, as in the general LCK case, you can have a definition in tensorial way. You have theta is already closed. It is the LCK form, and it must satisfy this formula. Maybe you remember you saw this formula for Vaisman. So this already tells you that all Vaisman manifolds are LCK with potential. On the other hand, this formula is equivalent with LCK with potential. It holds on Vaisman, but it doesn't imply Vaisman. And the proof is just it's a computation. It's not a complicated computation. I won't read it, but you have it here, and you will have the file. So one thing to remember is that unlike on Weissman manifolds, here you have just a distribution given by theta and I theta. They do not commute in general. So, and you don't know anything about their behavior, their commutation. So this distribution in general is not integrable. That is another good question. Classify the LCK manifolds on which this distribution is a foliation. It might be too general. I don't know. We tried. In any case, on LCK with potential, you don't have this foliation. Um, you can also have another definition in time of a in terms of a so-called d theta c potential. So instead of working with the differential, you work with the twisted differential, which was d minus theta wedge, and you look at functions defined on M. M is compact in general, so your functions will not be plurisubharmonic. So potential is a way of saying. So you can prove that there exists this true potential, positive and automorphic on the cover, if and only if the LCK form has this kind of LCK potential, say. Okay. Well, again, the proof is not complicated. It amounts to a commuting diagram for d and d theta. Here are the examples. As I've told you, the Vaisman manifolds you could see from the formula, but also you can show immediately that the potential is the norm of the Lie form pulled back, the norm with respect to the Kähler metric. But there are also non-Weismann examples. All non-diagonal Hopf manifolds, be them linear or non-linear. And all their complex submanifolds. So this is a property which is inherited. Here are examples showing that this LCK with potential class is strict. Of course, the blow-up, which contains projective lines, cannot have potential. Inoue surfaces also, it was proven by Ottiman. Euler-Klaus-Thoma manifolds, proven by Kasuya and Ottiman separately. So there are plenty of examples. I suppose also, I think Kato manifolds also are not LCK with potential. This is a very subtle and delicate point that we understood gradually. In our first paper, we thought that all potentials are proper. So we can have a restriction on the potential map on that phi. We can ask it to be a proper map in the very topological sense, to pull back compact to compact. And this proves to be equivalent with the deck group being the integers, that is with LCK rank 1. The proof is nice. Proof is nice, not very complicated. It amounts at identifying a fundamental domain for the group, and on the other hand, in the other sense, to see that if the group is not the integers, then its image is a dense subgroup in R plus, and disproving this by compactness is essentially. But let's just remain with this, that properness of the potential is equivalent with the deck group isomorphic with a cyclic group. This kind of LCK with potentials, this kind of manifolds LCK with potential, be it proper or improper, can be always in the end assumed to be proper. You can deform an improper potential to a proper one. And the approximation works in the C infinity topology. And here is a sketch of the proof. You work on the manifold with the so-called LCK potential, the one associated to d theta c. And because you want to arrive at a deck group isomorphic with Z, what you are interested in is the rational cohomology. So in fact, the idea is, as always, to look at the rational lattice and to intersect it with your directions. To move your direction such as to intersect the node. So, as in the Vaisman case, where we could deform to a Weismann structure to rank 1 structure, here we can do the same thing with an improper potential. So we again obtain rank 1, Z covers. Another good feature is that this class LCK with potential is stable to small deformations. That is because the plurisubharmonic condition is stable to small deformations. And this can be done via the previous deformation. You first go to proper potential, and then the proper potential, the proper PSH function is stable to small deformation. This was the initial motivation for us to introduce this class. We were looking for a class of LCK which is stable at deformations. Now, the cover, the universal cover, the Kähler cover of an LCK with potential has some particularity. We are always talking now about proper potential. So we talk about a Z cover. And what we could prove is that usually it is not complete manifold, but you can add only one point and you obtain a Stein variety. In general, what you add is a singularity. You can do this in dimension at least 3. it is because of our method of proof. Because we use this theorem proved separately by Rossi Andreotti and by Hsu. And our proof is inspired by complex geometry and algebraic geometry. We identify the manifold by its ring of good functions. So M will be in the end the spectrum of some bounded holomorphic functions. But something similar can be done also on surfaces if you accept global spherical shell conjecture. In any case, for surfaces, it's rather easy to see which can be LCK with potential to classify. You don't need this machinery. So for an LCK with proper potential, the Z cover in dimension at least 3 can be completed to a Stein variety. And you see, when you complete it with just one point, it's almost a cone, very similar to the Vaisman case when the cover is a cone. It's a cone over a Sasakian manifold. Now, it is a simile cone, but in fact, it is again a very close relation with algebraic geometry, but this is a bit more complicated, more subtle. I'll just describe it in words. We call this covering closed algebraic cone. You can define closed algebraic cones like this as affine varieties with a C star action with a unique fixed point, smooth outside that fixed point, and with this technical condition, think about a Hopf manifold, which is Cn minus 0, which you complete with one point to Cn, and you have a contraction with a fixed point 0, and so on. But what is more interesting is that for the moment we know that only that it is a Stein manifold, the completion. In fact, you can prove that it is exactly what in complex geometry it is called the Stein completion. It is in fact the weak Stein completion in Hsu's terms. But it has also an algebraic structure. It is an affine variety. And the algebraic structure, it will be more transparent on the next slide, but the algebraic structure can be made explicit. You can put the hand on the regular functions. They are all the gamma finite functions, where gamma is the generator of the deck group, seen as a group of automorphisms of this Stein completion. The gamma finite means that when you act with gamma as an endomorphism on the vector space of functions, this cyclic group, say, obtained by iterating the action of gamma is finite dimensional. So these are the regular functions. And more striking is that this algebraic structure, the set of regular functions, is unique. What does it mean? You can have two different LCK manifolds with the same covering, but with constructions differing, with different generators of Z. They will give you two different LCK structures, but the algebraic structure of the cone of this Stein completion stay fixed. And it is related to a projective manifold or orbifold, because what we could prove using this Stein variety was that any compact LCK manifold with potential can be holomorphically embedded in a Hopf manifold, and vice versa. And the idea was exactly this one. You complete the covering with one point to a Stein variety, you embed the Stein variety in a CN, then you find a automorphism which commutes with the projections of your covering and with the projection of Cn to a projective manifold. To a Hopf manifold, sorry. And on the other hand, when you are in Cn, when you included your cover in Cn, this action that you started with, this action here of rho, can be extended, and it will give you a projective space with some weights, and your manifold in the end proves to be related to a projective manifold, a subspace of this projective, of the complex projective space with weights. You had the algebraic cone, the open algebraic cone, which is exactly the universal cover of your LCK manifold. And this can be understood as the affine cone of a projective orbifold. This is roughly speaking the picture, but technically it is more complicated to explain. Coming back to this theorem, which can be understood as it is. LCK is potential. It can be taken as an equivalent definition. LCK with potential is a holomorphic a complex submanifold or even subvariety in a linear Hopf manifold. That's all. And it is of Vaisman type if and only if it can be embedded in a diagonal Hopf manifold. This theorem was extended in the locally conformally symplectic type, the embedding, by David Martinez Torres. You can apply this embedding theorem in different situations. We applied it to show that even nonlinear Hopf manifolds are LCK with potential by embedding a nonlinear Hopf manifold in a linear Hopf one. We obtained also a embedding theorem in Sasaki geometry. That's a CR embedding in spheres. And the embedding preserves the respective Reb fields. Uh, LCK with potentials can be deformed to Weisman. That's important because it tells you that the topology is the same. Again, our method works in dimension greater than 3 by the same reason. We use Andreotti's U. And the idea here is not simple, but you take the linear Hopf manifold in which your manifold is embedded, and you decompose the matrix into unipotent and semilinear semi-simple part, and then you look at the orbit of the semi-simple part. This can be explained more using Teichmüller space, and it can be given the following more precise formulation. Compact LCK manifold, dimension greater than 3. Then you have a Weisman complex structure that its point, the point that it defines in the Teichmüller space, belongs to the closure of your initial stuff, your initial complex structure. So that's the meaning. Well, you can say this also using non-separability. You cannot separate a point in the Teichmüller space from points which correspond to Weisman type structures. And this is important. If you are on a Weisman manifold and you have other LCK structures with potential on the same space, the leaf form corresponding to the Weisman structure is automatically a leaf form for LCK with potential with respect to another complex structure. There are different criteria for the existence of LCK metrics with potential. One of them is a way of relaxing the result they had with Kamishima about holomorphic and conformal flows. That was a C action. You take just a part of it. You take just as S1 action, and you have the same condition to lift to true homoscedasties to the Kähler cover. And this is enough to show that you have a potential on the cover. Essentially, it's enough to have Botchan class 0. The Botchan class of the fundamental form is 0, and then you build the potential. But it's not necessarily positive, and then you have to show that you can make it positive. But the converse of this theorem is also true. But it's very involved, and it needs the construction of the logarithm. This is the criterion with the Botchan class. when we published it, we made a mistake. It wasn't positive. We just showed it is a potential. It wasn't positive. And then we proved that you can always can have a positive one. But in fact, Nicolina showed us that our potential was positive, but you had to work to prove it, and she did it. Um, you can say something on the set of Lie classes, as I told you in the first part of this talk. When you have an LCK manifold, you are interested in this space L, which is a priori it is a subset of H1. For Inoue, it is a singleton, and also for earlier Klaus-Thoma. But for Weisman manifolds, it is a half space. And we proved that the same holds for LCK with potential, again in dimension bigger than 3, because we need deformation theorem. And in particular, yes, we have also the vanishing of the topology. So this is another proof. Well, here's the proof is more involved. We cannot anyway. One can see the proof. The last slides. I can I have 5 minutes, Ethan?
Yeah, you can. Yeah, go to 11. That's fine.
What I want
Or
now is
11
to.
Eastern.
Okay, thanks.
Yeah.
What I want is to tell you how can we classify the say the known examples of LCK manifolds, and to give you a result about products. So let me call LCK manifolds of Inoue type the following objects. You look at a PP form and you say that it is weakly positive if when you wedge it with any Hermitian form at the necessary degree, necessary power, the result is non-negative. It's a technical condition, but you will see. So let's suppose you have such thing on an LCK manifold. And you say that this weakly positive consumes the LCK structure if this weakly positive eats any cohomologous form with the Lie form. And the Inoue type, what we call Inoue type LCK manifolds, is a manifold which admits such a form, weakly positive, which is also closed. And this is the fact that OT and LCK Inoue surfaces are of this type. And we can explicitly write this weakly positive form. You don't need to bother with this computation here. Just you have such a strange form. Um, all the LCK manifolds that we know at the present day are of one of these three types. They have potential, or they are of this type that I described, or they have curves, rational curves. For example, these classes are not mutually exclusive. For example, the blow-ups have rational curves, the Kato manifolds have. But when you blow up something of this kind of Inoue type, you obtain again something of Inoue type. This can be proved. So they are not mutually exclusive. But these are three classes that exhaust the known LCK manifolds now. And a problem which is open still is what to do with the products. You know that it's clear that product of two conformal structures is not conformal. So you wonder what can be done on a product of two LCK metrics, of two LCK manifolds. What kind of structure can you have? Maybe you can have an LCK structure, but of course not the product one. You want to fix the complex structure as the product one and to look for metrics. And what we could prove together with Vuletescu and Misha is that a product of two complex compact manifolds in which one factor is in one of the above classes cannot have LCK structure. In particular, a product of known LCK manifolds cannot be LCK. And for surfaces, if you admit the GSS conjecture, we can have this statement, which is sharper. In the same vein, there is a result by Nicolina. We avoided curves in what we did. Nicolina did not avoid it. So she proved that the product of a complex curve is an LCK manifold is LCK only when you start with potential. Well, I apologize. I was too long. So thank you. I shall stop here.